What is the specific problem that the proposed method aims to solve based on the student's paper?
The specific problem that the proposed method aims to solve, based on the student's paper, is to evaluate the capabilities of language models, LMs, in probabilistic reasoning tasks, specifically in estimating percentiles, drawing samples, and calculating probabilities for both idealized and real-world distributions. The paper aims to assess whether LMs can accurately answer questions about distributions, understand the impact of providing different types of prompts within distribution family shots, and determine if LMs simply repeat in-context examples or exhibit more complex behavior like interpolation. Additionally, the method aims to explore how real-world context influences LM performance in probabilistic reasoning tasks and whether simplifying assumptions, such as using a normal distribution approximation, can improve LM performance. The paper also investigates the effects of providing real-world context and parametric assumptions on LM performance compared to providing a few shot examples. Ultimately, the proposed method seeks to enhance LM performance in probabilistic reasoning tasks across a variety of distribution types and domains by leveraging different types of prompts and contextual information.
How does the proposed method work, and can you illustrate it step by step?
The proposed method works by evaluating the probabilistic reasoning capabilities of language models, LMs, through three distinct tasks: estimating percentiles, drawing samples, and calculating probabilities. 1. Estimating percentiles. In this task, the LM is given a distribution and asked to determine the percentile a sample would appear in. The target percentiles range from 1 to 99, and the LM's responses are sampled 10 times. The performance on this task varied across distribution families, with the best zero-shot performance seen for uniform and normal distributions. 2. Drawing samples. Here, the LM is tasked with randomly drawing samples from a given distribution without using additional tools. The LM's responses are expected to be numerical, and this task is repeated 1,000 times per distribution to assess performance. 3. Calculating probabilities. In this task, the LM is asked to calculate the probability that a sample falls between two given values in a distribution. The target probabilities range from 0.1 to 1. 0, and the LM's responses are expected to be numerical. The method also involves evaluating the impact of real-world context on LM probabilistic reasoning by exploring distributions from domains like health, finance, and climate. The performance of LMs is assessed in zero-shot settings across these real-world distributions, with prompts containing information about the data source, year, and any relevant filtering done. The method further investigates the effects of providing prompt examples from different distributions in the same family, or samples from the same distribution. It compares the performance when providing within-distribution shots versus within-family shots, showing that within-distribution shots have a more significant impact on LM performance. Additionally, the method explores the use of simplified assumptions, such as a normal distribution approximation, to improve LM performance on real-world distributions. It compares the performance of providing a normal approximation versus providing 3 few-shot examples, showing that both strategies can enhance LM performance, with the few-shot examples generally performing better. Overall, the method systematically evaluates LM performance on probabilistic reasoning tasks across idealized and real-world distributions, considering the impact of context, prompt design strategies, and the use of simplified assumptions to enhance LM capabilities in probabilistic reasoning.
What are the theoretical or practical benefits of using the proposed method, according to the paper?
The theoretical and practical benefits of using the proposed method outlined in the paper include 1. Improved numerical reasoning. The method enhances language models' capabilities in handling numerical reasoning tasks, which have been a challenge for traditional language models. By incorporating prompts and examples tailored to numerical tasks, the models show improved performance in tasks such as estimating percentiles, drawing samples, and calculating probabilities. 2. Enhanced probabilistic reasoning. The method focuses on developing language models that can reason over sets and understand distributions, which is crucial in various fields such as population health, climate, and finance. By training the models on a diverse set of idealized and real-world distributions, they can better grasp probabilistic concepts and provide accurate answers to questions about distributions. 3. Contextual understanding. The method emphasizes the importance of context in probabilistic reasoning tasks. By providing real-world context and simplifying assumptions, like the normal distribution approximation, the language models can leverage this additional information to improve their performance on real-world distribution datasets. 4. Efficient data interpretation. By training language models to reason probabilistically and understand distributions, the method enables more efficient data interpretation. Language models can summarize data with a small number of parameters, leading to quicker and more accurate insights from complex datasets. 5. Generalization to various domains. The method's approach of evaluating language models across different domains, such as health, finance, and climate, ensures that the models can generalize well to diverse real-world scenarios. This generalization capability is crucial for practical applications where models need to perform effectively across different domains. 6. Adaptability to different distribution families. The method's evaluation of language models across 12 families of idealized distributions demonstrates the model's adaptability to different distribution types. This adaptability is essential for handling a wide range of data types and scenarios in real-world applications. 7. Performance enhancement with additional context. The method shows that providing additional context, such as real-world information and parametric assumptions, can significantly improve language models' performance on probabilistic reasoning tasks. This enhancement can lead to more accurate and reliable results in practical applications. 8. Efficient prompt design strategies. The method introduces efficient prompt design strategies that leverage real-world context and simplified assumptions to boost language models' performance. These strategies can streamline the model training process and improve overall efficiency in handling probabilistic reasoning tasks. 9. Validation of assumptions. By comparing the performance of language models with and without simplified assumptions like the normal distribution approximation, the method validates the impact of these assumptions on model performance. This validation ensures that the models are making informed decisions based on the provided context and assumptions. 10. Overall performance improvement. The method's comprehensive evaluation and analysis of language models' performance on probabilistic reasoning tasks demonstrate an overall improvement in accuracy and efficiency. This improvement signifies the practical benefits of using the proposed method in enhancing language models' capabilities in handling numerical and probabilistic tasks effectively.
How were the methods validated or tested in the paper?
The methods in the paper were validated and tested through a series of experiments using language models, LMs, across idealized and real-world distributions. The validation process involved evaluating the zero-shot performance of 4 LMs, Gemini 1, 0 Ultra, GPT-4 Turbo, GPT-3, 5 Turbo, and Llama 3-70B on 3 probabilistic reasoning tasks, estimating percentiles, drawing samples, and calculating probabilities. The LMs were tested on 12 families of idealized distributions and real-world distributions from the domains of health, finance, and climate. The experiments included providing prompts with and without additional context, such as real-world information and simplified assumptions like a normal distribution approximation. The performance of the LMs was assessed based on their ability to accurately answer questions about distributions in a zero-shot manner and with the inclusion of different types of prompt examples. The results were analyzed to determine the impact of context, prompt design strategies, and the effectiveness of simpler assumptions on the LM's probabilistic reasoning capabilities. The experimental setup and results were detailed in the paper, to provide insights into the performance variations and improvements observed across different scenarios and distributions.
What were the specific results achieved with the new method in the paper?
The specific results achieved with the new method in the paper include 1. Language model, LM. Performance varied considerably across families of distributions in the idealized distributions dataset. Zero-shot performance on estimating percentiles task was best for the uniform and normal distributions. 2. Providing within distribution shots improved LM performance substantially across all tasks, estimating percentiles, drawing samples, and calculating probabilities. 3. LM performance exceeded the nearest in-context baseline, indicating that LMs perform some form of interpolation rather than simply repeating in-context examples. 4. In the real-world distributions dataset, LMs showed varying degrees of zero-shot performance depending on the context. Gemini 1. Zero Ultra had superior zero-shot performance in the climate domain, while GPT-4 Turbo performed better in the health domain. 5. Adding real-world context improved LM performance on average, with real-world context and a normal approximation further enhancing performance. 6. Parametric assumptions such as a normal approximation as a prompt design strategy consistently improved performance on real-world distributions. 7. Providing 3 few-shot examples generally resulted in better performance compared to using a normal approximation, especially across health, finance, and climate datasets. These results demonstrate the effectiveness of the proposed method in enhancing LM performance on probabilistic reasoning tasks across both idealized and real-world distributions.
What are the limitations or drawbacks of the proposed method according to the student's paper?
The limitations or drawbacks of the proposed method as outlined in the student's paper include the following. 1. Limited generalizability. The paper focuses on evaluating language models' probabilistic reasoning capabilities on specific tasks and distributions. This may limit the generalizability of the findings to a broader range of tasks or distributions not covered in the study. 2. Assumption of idealized distributions. The study heavily relies on idealized distributions, such as normal, log normal, and others, which may not fully capture the complexity and variability of real-world data distributions. This could lead to potential discrepancies when applying the findings to real-world scenarios. 3. Simplified assumptions. The use of simplified assumptions, like treating real-world distributions as normal distributions, may not always be appropriate or accurate. Some real-world distributions, such as power law distributions, may not align well with the normal approximation, leading to potential inaccuracies in the model's performance. 4. Dependency on training data. The performance of language models in probabilistic reasoning tasks is heavily dependent on the training data they have been exposed to. Models like Gemini 1, Zero Ultra, and GPT-4 Turbo show varying degrees of zero-shot performance based on the amount and quality of training data they have received. 5. Performance variability. The study highlights that the performance of language models can vary significantly across different tasks, distributions, and contexts. This variability could make it challenging to consistently rely on these models for accurate probabilistic reasoning in all scenarios. 6. Complexity of real-world data. Real-world data distributions, especially in domains like health, finance, and climate, can be highly complex and multifaceted. Simplifying these distributions to fit idealized models may oversimplify the underlying dynamics, leading to potential inaccuracies in the model's predictions. 7. Need for further validation. While the study provides valuable insights into language models' probabilistic reasoning abilities, further validation and testing across a wider range of distributions and contexts are necessary to ensure the robustness and reliability of the proposed method. 8. Interpretability. The paper does not delve deeply into the interpretability of the language model's decisions in probabilistic reasoning tasks. Understanding how the models arrive at their answers and whether these processes align with human reasoning could be a potential limitation. 9. Scalability. The scalability of the proposed method to more complex or larger datasets is not extensively discussed. As the complexity and size of the data increase, the performance of the language models may be impacted, posing a limitation to the method's applicability in real-world scenarios. 10. Ethical considerations. The paper does not address potential ethical implications of using language models for probabilistic reasoning tasks, such as biases in the data, fairness and transparency in decision-making, which are crucial aspects to consider when deploying such models in practical applications.